Hello, welcome to this video on the directional derivative and how it's related to a vector called the gradient. In this video, we'll go through the concept of the directional derivative, why the formula is what it is, and then in subsequent videos, we'll look at some examples. All right, so if you're looking for the why, please watch this video. All right, great. So we start off with a multivariable function that's explicitly defined. Z is a function of x and y. And we talked about in previous videos how the x partial derivative is the rate of change of the function in the direction that is parallel to the x-axis. And so here's a blob that represents the graph of this particular function. And we have a line at the point 1, 1, 1. And we have then the number that you get from taking the x partial derivative at that point is going to be represented by the slope of that tangent line to the curve. See, y is stuck on 1, so that plane that comes through is at y equals 1. And so it's the x that's changing. Y is stuck on 1. When you take a partial derivative, you leave the other variable as a constant. All right. And so we also saw that the y partial was the rate of change of the function in the direction parallel to the y-axis. And so you just let x be stuck on that constant. You cut it with a plane. You have a curve, and then you have the line that comes down. That slope of that line is what you're measuring when you get the partial derivative of f with respect to y at that point. So these are two directions. If you're standing at that point, 1, 1, 1, you could step in the direction of the x-axis or the negative x-axis. You could step in the direction of the y-axis or the negative y-axis. And so what about other directions? You see, these directions should be tied to a vector. So if you're stepping in the direction of the y-axis, your x-axis, then you're stepping in the direction of the I vector or minus I or anything parallel to that. If you're stepping in the direction of the y-axis, then you're stepping in the direction of j or minus j or anything parallel to that. So you give me a vector and I'll give you a directional derivative. On the next slide, let's see how that works. So we want to be able to find the rate of change of our function at a particular point in a direction of some arbitrary unit vector. The vector needs to be a unit vector. So you have some surface, z is a function of x and y, and you have some point. When you plug in x naught, y naught, you get out z naught. Okay, so that's a point that's on the surface, x naught, y naught, z naught. This is a picture where we have the point, we call it P. All right. And then the direction vector is two-dimensional. It's in the XY plane, the vector AB. And so that's the vector down there in the XY plane. It's called U. It's a unit vector. That tells you which direction that you're stepping. So you're stepping in the direction of the U unit vector. Okay. So then just like with the x partial and the y partial, we slice with the plane in that direction. So we slice with the plane, and what happens then when you slice with the plane is your multivariable function becomes just basically a single variable function. So when you slice, we'll get a curve. That curve is labeled here as C. Okay. And so the vertical plane that passes through the point P in the direction of U intersects the surface at C. That's our curve there. And so when we get the directional derivative, we are getting the slope of the tangent line to that curve in that direction. All right. Whenever we do derivatives, what we do is we take the point that we're interested in taking the derivative at, and we have another point. So let's label this other point Q. It's any other random point that's also on the curve, which is also on the surface, which is also on the plane, all that at the same time. Okay. And what we're going to do with this point, basically, like when you do derivatives, you let the one point approach the other point, and you do a limit. That'll give you the secant line slope, and then from there you get tangent line slope. And so here's how it's going to work in relation to this. So Q is another point that's on the curve. We project down onto the XY plane. So the point P projected down is called P prime. The point Q projected down is called Q prime. And what's going on there is that when you're projecting down, you're letting the z coordinate be 0. So the point P prime is at x naught, y naught, 0. And the point Q prime is at x, y, 0. Okay, they both are on the vector u. Okay, but they might not be a distance 1 apart from each other. Okay, let's call the distance that they are apart from each other h. Okay, and so it's a the vector that connects P prime to Q prime is a scaled version of u. Okay, and that scalar we'll call h. And h is the magnitude there of the vector that connects P prime to Q prime. All right, that vector then, because it's a scaled multiple, it's a multiple of the vector u, we can call it HA and HB. When you scale a vector, you scale each component. All right, you guys are doing great. So it's a vector. So we have the I and j components of that vector are HA in the I direction and HB in the j direction. All this is going on down in the XY plane. Okay. All right, you're doing great. Now, the HA is basically the difference between the x and the x naught. And the HB is the difference between the y and the y naught. The coordinates of the vector P prime, Q prime would be x minus x naught and y minus y naught. You know, you have 2 points, and we'll find a vector between those 2 points, terminal minus initial on each coordinate. So x minus x naught and y minus y naught. X minus x naught is your I component, and y minus y naught is your j component. So then what you can do is solve for x. If HA is x minus x naught, then x is x naught plus HA. If HB is y minus y naught, then y is y naught plus HB. And you could, you don't have to, but you could take this function and rip out the x's now and put in x naught plus HA, and rip out the y and put in y naught plus HB. Okay? All right, it's okay if you don't follow this. I just want you to understand, hopefully, where the formula is coming from. And right now, we're going to give the definition of the directional derivative. It's going to be the limit, okay, as h goes to 0. Remember what h was? The distance between the P prime, Q prime in the XY plane. As h goes to 0, up on the curve, what's going on is Q is headed towards P. I'm sorry if that's too small, but and so h is going to 0, and then what you have is then the up on the curve. Let's go back to the curve. All right, the difference there. We have the function is x naught plus, so we have x naught plus HA and y naught plus HB in the formula here. That's the f of, the f of xy, and then it's minus the f of x naught y naught, and it's all divided by h. That's the secant line slope. Okay, the f of xy, that's the point P. I mean the f of xy, that's the point Q, and the f of x naught y naught, that's the point P. Up on the curve we're talking about. And so we subtract their z values and we divide by h, and what we're getting is the slope of the red line. We're going from secant line slope to tangent line slope by letting h go to 0. So that line is labeled as capital T here. So that's it. We found an expression for the slope of that line, but it's not going to be the one we actually use. It's impractical to have to deal with that. On the next slide, I just showed the proof that connects this to the more usable formula. The more usable formula is, I'm sorry, I didn't say this. The symbol for the directional derivative is a capital D. And then there's the function at whatever point you want to find the directional derivative at. And then in between, there's a subscript of U. That's the directional, that's the direction in which you're stepping. Okay, so D sub U of F. Okay. All right, so there's this vector that we can use instead that would make this much more easier to calculate. And that vector is called the gradient. All right, the gradient is a vector that's full of partial derivatives. So the I component is the fx, the x partial, and the j component is the fy, the y partial. It's called the gradient, and it's strikingly useful throughout the process of these next 2 or 3 videos. You'll see that the gradient is used very, very often. It's used to be, first off, it's used to be able to calculate a directional derivative. And we love to calculate things that are simple. And so this is a simple calculation. It's a dot product. The directional derivative can be calculated by taking the dot product of the gradient with the unit vector. It's that simple. All right, we've gone over our 10-minute mark. But this is the calculation. I'll show you why it's the calculation on the next video. I don't want to go too far past 10 minutes. But you just take a dot product between the gradient, evaluate it at your point on x naught, y naught, dot it with the unit vector. If someone doesn't give you a unit vector, that's okay. You can make it unit vector by dividing by its magnitude. All right, great. So that's the formula. I have to, on the next video, show you how these 2 blue formulas are connected, the definition and the shortcut formula. I'll show you how that's connected, and we'll take a look at that on the next video. Thank you for watching. My name is Nakia Rimmer, helping you through this journey of vector calculus, multivariable calculus. It's all that. It's Calc 3. And be sure to ask me any questions if you don't understand anything. Comment down below. Reach out to me. Like and subscribe, and I'll see you in the next video.